In this video, we are going to learn how to evaluate the line integrals of vector fields. To motivate this, recall the work done by a constant force F in moving an object over a displacement d is defined as the dot product of the two vectors. So W equals F dot d. Now our goal is to expand upon this definition by letting the object move along a curved path in space, so that we're no longer restricted to a linear path between 2 points. Instead, we can choose any path that we want between those same 2 points. At each point along the curve, both the direction the object moves in and the force acting on it can change. So that's the other variation here. We're not restricted to a constant force acting on the object. The force acting on the object can change as we move along the curve, and that's going to be based on the vector field. So let's draw a picture to visualize what we're describing. So we have a curve C, right? So that's our curve C. And let's say we start at t equals a, we go to t equals b. So the direction we're moving in is shown by those two little arrows. And we'll say that c is parameterized by the vector function r of t. So that's the curve that we want to move along. Now we also have a vector field. So we'll start by defining a few vectors at points on the curve. And remember, it's not constant, so the vectors can change direction, they can change magnitude as we move in space, right? And we don't have to just have vectors along the curve. Really, there are vectors everywhere in space. We want to focus on the vectors that start at the points on the curve. So let's highlight one of those points, and let's compute the work at that point. So we have a force vector given by this vector of the vector field, and then we have a direction vector, and that's going to be the tangent vector to the curve. Now we could use r prime to denote this vector. That would work, but it would be more helpful if we had a unit tangent vector. Since we don't really want the magnitude of the direction to play a role in our computation, we just want it to give direction, and we want the magnitude to come from the force. So we have that vector. It's called the unit tangent vector. If you recall our work earlier in the course with vector functions r of t, we defined the unit tangent vector with a capital T. And now we want to compute the work. So really what we're trying to figure out is how much of the force vector goes in the direction of the unit tangent vector. And that's nothing more than a scalar projection, which would be the dot product of f and t. Now remember, this is happening in an infinitesimally small region around the point. We're just drawing the vectors bigger so we can visualize them. But that's only at one point, and we need to continue along the curve, so we'd have to do it here, right? There would be our unit tangent vector, project down, compute the scalar projection, and keep going. Now, how do we accumulate all the computations that we're going to have along the curve? That's going to be an integral. More specifically, a line integral is going to be the tool that we use here. So the work done by a force field or a vector field in moving an object along a curve C can be defined as the integral along C of that dot product we defined at that single point, f dot t, so the vector field dotted with the unit tangent vector. And then we're moving along an arc length, so we're integrating with respect to s. Now, as we saw in the previous video, it's easier for us to evaluate a line integral in terms of t than it is in terms of s, or with respect to arc length. So we can make some substitutions here. So t, the unit tangent vector, is r prime of t over the magnitude of r prime of t. So we can say integral along C of f dotted with r prime of t over magnitude of r prime of t. And then if we recall, ds is the magnitude of r prime of t dt, right, which is the arc length computation. So that's our ds. This is t. And what you may notice is that the magnitude of r prime of t is going to simplify here. And that's going to leave us with the integral along C of f dot r prime of t dt. So now we have everything in terms of t and a much more condensed version. Really what this is telling us is to take the dot product of the vector field with the tangent vector r prime. Now notationally we can clean this up a little bit more. If we write r prime of t as dr dt, then we can say that r prime of t dt is dr, so integral along C of f dot dr. This is the notation that you're going to see most frequently when we're evaluating line integrals of vector fields. So let's formally define this idea. So let f be a continuous vector field defined on a smooth curve C, parameterized as r of t, where t is bound from a to b. Then the line integral of f along C is, as we just wrote, the integral along C of f dot dr. Now, if we were trying to evaluate it, working in the other direction of what we just wrote, what we're going to do is we're going to define the integral from a to b. We're going to redefine the vector field in terms of t. So that's what this is showing us. Right? The vector field right now is in terms of x and y, or x, y, and z, whether it's 2 or 3 dimensional. We need to get it in terms of t, in terms of a single variable. And then we can replace that dr back with the r prime of t dt. So find the tangent vector, redefine our vector field in terms of t, compute the dot product, and then evaluate the integral. Those are the steps that we're going to go through to evaluate the line integral of a vector field. Now, continuing on the theme of work, determine whether the following integrals are positive, negative, or zero. So really just emphasizing this idea that the integrals represent work. We have 4 different paths in this vector field, and we want to determine the sign of each integral, or if it's zero. So if we move along curve C in this vector field, what you'll notice on the first half, the vectors kind of push against the object, but then once it moves into the second half, the vectors are pushing with the object. And it seems, just visually, to be the same amount against as it is the same amount with. So if we accumulate work over the whole curve, it looks like it's going to sum to be zero. Right? Negative work on the first half, positive work on the second. Now, if we go along curve D, now the direction we're moving is against the vector field. So the vector fields are pushing against us. So that means that the work done by the vector field is going to be negative, because they are pushing against us as opposed to pushing with us. Whereas now if we look at curve E, the vectors in the vector field are now pushing with us. So we should expect that work to be positive. And then the last one, if we go along the closed curve F, it looks as if those vectors are perpendicular or orthogonal to the curve. So that means that this is going to be zero. Because if you remember, take that dot product approach, if you drew the tangent vector at any point and dotted it with the force vector from the vector field, 2 vectors that are orthogonal, dot product is 0. So basically the work computation at every point along this curve is going to be 0. And this is just helpful as we navigate through these integrals to give us a sense of what each answer represents. When we get a positive answer or a negative answer or an answer of 0, what it actually means. Okay, so now that we have set up the conceptual part, we've talked about how to evaluate it. Let's actually evaluate some. Evaluate the integral along the curve C of f dot dr, where f is the vector field yx and c is the line segment from 0, 3 to 2, 1. So here they did not give us a parameterization, so that's the first thing we should do, parameterize the curve in terms of t. So our direction vector is going to be 2, negative 2. That makes r of t equal to 2t, 3 minus 2t. And the bounds on t would be 0 to 1, just how we built the direction vector. we're going to start at 0, 3, and that vector is going to take us to 2, 1 when t is 1. We can always change this. If you use a direction vector of 1, -1, for instance, then your t-bounds would be 0 to 2. That's not going to affect the problem, right? We explored that a little bit in the previous video. Then r prime of t is going to be 2, -2. So we have our tangent vector. We need to redefine our vector field. So we need our vector field in terms of t. And we're going to use the parameterization to do that. So remember, this is x and this is y. So we have 3 minus 2t, 2t. Now we have all of the components. We need to evaluate the dot product of f with r prime. So that's going to be 6 minus 4t minus 4t. And now we can set up the integral. So the integral from 0 to 1 of 6 minus 8t dt. We get 6t minus 4t squared, evaluated from 0 to 1. 6 minus 4 is 2. Okay, so what this means is the work done by this particular vector field in moving an object or a particle on this particular curve in the direction they gave us is going to be 2. Now, what happens if we switch the order? So what if we went from 2, 1 to 0, 3? Well, if we got positive work in the first orientation, then we should expect this to be negative. But let's verify that to be true. So the direction vector is going to be -2, 2 now. We need to parameterize our curve. So this is going to be 2 minus 2t, 1 plus 2t. So the parameterization does change. We're still bounding t from 0 to 1. R prime of t is going to be -2, 2, or that direction vector. We need to redefine the vector field in terms of t. So remember x and y. So we have 1 plus 2t, 2 minus 2t. Now we can compute the dot product. So f dot r prime of t is -2 minus 4t plus 4 minus 4t. So we have the integral from 0 to 1 of 2 minus 8t dt. So we get 2t minus 4t squared from 0 to 1. 2 minus 4 equals -2. So now it's the negation of the value we got on the previous slide. So that's actually an important result that we can build off of. The fact that when we changed the direction, we got the negation of the value. So line integrals of vector fields depend on the direction that the particle transverses the curve. We define this as the orientation of the curve. And this is going to appear in different ways in different problems. It could be simply start at this point, go to this point. They could tell us that we're moving in a clockwise direction or a counterclockwise direction. So it's going to vary in each problem. Now the nice part about the result we just saw is if C is an oriented curve and -c is the same curve but in the opposite direction, then the integral along -c of f dot dr is just the negation of the integral along c of f dot dr. So it's going to be important to check the parameterization we create for a curve C matches the stated orientation. If it doesn't, we have two options. Either define a new parameterization or stick with the one that we created if it's just in the wrong direction and then negate our line integral. And oftentimes that's the easier way to evaluate the problem because we already have a parameterization. If it's just going in the wrong direction, negate the line integral that we're evaluating. So let's see what that looks like. Evaluate the integral along c of f dot dr, where the vector field is x plus y, 2y, and c is the unit circle x squared plus y squared equals 1, oriented clockwise. So we'll start by parameterizing the curve. Let's ignore the orientation for a second. So we parameterize the unit circle. So we'll say cos t sine t is just a standard way to parameterize a circle of radius 1, and the bounds on t would be 0 to 2 pi. Now the problem with this parameterization is we're going to be moving in the counterclockwise direction, right? So this is going to be counterclockwise, CCW. We want to orient clockwise. So again, we have two options. We can change our parameterization. For instance, we can negate sine of t, and that's going to move down in the clockwise direction as opposed to up to start. Or we could just stick with this and negate our line integral, which is the option I'll choose to use here. So then we continue on with the problem. So r prime of t is going to be negative sine of t cos t. We redefine the vector field, which in this case is cos t plus sine t, and then 2 sine t. Now we dot the vector field with r prime of t. So we get negative sine t cos t minus sine squared t plus 2 sine t cos t. Now we do have to remember that we are setting up the negation of the integral. It's very easy to forget that fact, right? So maybe you want to make a note to yourself if you're choosing the wrong orientation, or if you think you're going to forget, then I would go with option 1 and create a new parameterization. So we're going 0 to 2 pi of sine t cos t minus sine squared t dt. Okay, so in order to integrate this, we can distribute the negative in, but I'll leave it out just really for emphasis. We need to replace the sine squared, so we have sine t cos t minus the double angle formula for sine is 1/2 minus cosine 2t over 2. So if we distribute the minus, we get minus 1/2 plus cosine 2t over 2 dt. So now we integrate. So the first term, underline sine of t as our u, du would be cosine of t. So we have the negation of 1/2 sine squared t, then minus t over 2, and then integrating here, underline 2t, the derivative would be 2. So we get plus 1/4 sine of 2t. We're going to evaluate that from 0 to 2 pi. So that's going to be the negation of sine of 2 pi is 0, then minus pi, then sine of 4 pi is 0. And if we plug in 0, all three terms are 0. So we just get pi here. And just something to note, I like to do the dot product before setting up the integral, but of course you can do them at the same time. You can do the dot product while setting up the integral. Just make sure all your terms have the right sign and the right values as you proceed. Now the problem changes a little bit. Compute the work done by the vector field, 1 over x plus y, 1 over xy, to move an object from 1, 1 to 16, 4 along the curve r of t being t squared t. So they don't explicitly tell us the line integral we're evaluating, but when they're asking us for work, really this is asking us to evaluate that line integral along c of f dot dr. So the same steps that we've been taking, but we just have to know the form of the integral we are evaluating. So we already have our parameterization, which is nice. So let's just get our t bounds out of the way. So this would be t equals 1. This would be t equals 4. Right? So t goes from 1 to 4. Our prime of t is going to be 2t1. Then we need to redefine the vector field in terms of t. So that's going to be 1 over t squared plus t, 1 over t cubed. Then we're going to dot that with our prime of t. So we get 2t over t squared plus 2, t squared plus t rather, plus 1 over t cubed. So then we can say we have the integral from 1 to 4 of 2 over t plus 1 plus, I'll write this as t to the negative third just for integration purposes. So that first term is a natural log type integral, so 2 natural log of the absolute value of t plus 1. And then here we'd have t to the negative second divided by negative 2, so minus a half, evaluated from 1 to 4. So that's going to be 2 natural log of 5 minus 1 over 32 minus 2 natural log of 2 plus 1 half. And if we wanted to condense this answer even more, we can condense the two log terms, natural log terms, with our log rule. So that's going to be 2 natural log of 5 over 2. And then 16 minus 1, so plus 15 over 32. And this would typically be an answer that an answer key would produce, the most condensed version of what we just got. So the last thing we have to talk about is another way that we can see the work integral written, that integral of f dot dr. So if c is a curve parameterized by r of t being x of t, y of t, where t is bound from a to b, and the vector field has components p of xy and q of xy, then we can express the line integral a bit differently. So what we're going to do is we're going to write the integral along c. We're going to replace f with the vector field. So p of xy, q of xy. And then we're going to dot it with r prime of t, which is x prime of t, y prime of t, and then dt. And then if we evaluate this dot product, we're going to get the integral along c of p of xy, x prime of t, plus q of xy, y prime of t, dt. And then we can distribute the dt to both terms here, and you'll see why. We're going to do that in a moment. So it's going to be p of xy, x prime of t dt, plus q of xy, y prime of t dt. And the reason for doing that is we're going to replace the x prime of t dt and the y prime of t dt. So if we think x prime of t can be expressed as dx dt, and then similarly y prime of t equals dy dt. So very similar to earlier in this video, dx then would be x prime of t dt. So we can write this as the integral along c of p of xy dx plus q of xy dy. And this is what we call differential form of the line integral. And it's important that we can recognize it because one of the theorems that we're building towards presents the line integral of the vector field in this way. So we have to know when it's the integral of the dx and the dy, really these components of the integral are the components of the vector field that we're dealing with, right? And as far as evaluating, it can change things a little bit, but we're still finding all of the same vectors that we were before. If we extend into 3 space, all that's going to change is now our vector field has 3 components. So now the differential form has a dx, dy, and a dz, and each component is a different component of the vector field, p, q, and r, respectively. So let's look at setting one of these up, and then I'll give you the answer. We won't actually go through the integration, as I think you'd be able to do it. So evaluate the integral along the curve c of negative 3y dx plus x dy minus 4z squared dz. So again, just to highlight, these are the components of the vector field. So our vector field is negative 3y x negative 4z squared. They give us our parameterization, they give us our t-bounds. So next thing we can do is we can find our prime of t. So that's going to be 2t plus 3, and e to the t. We need to redefine the vector field in terms of t. So I'll stick with the same colors here. So we have negative 3 times t squared plus 3t, right? X, y, and z now. X is 2t plus 3, and then we have negative 4e to the 2t. Okay, so now if we're setting up our integral, we can do f dot r prime, but if we stick with this here, this is really dx, this is dy, this is dz. Each term would have a dt component with it as well. So we're going to have the integral from 0 to 1 of negative 3 times t squared plus 3t, and then dx dt would be 2, and I'll leave the dt for the end. We'll just treat it as a term we factored out. So that's our first term. Then we have the x, so 2t plus 3. dy is 2t plus 3 dt, so another factor of 2t plus 3. And again, we'll save the dt for the end. And then minus 4e to the 2t, dz is times e to the t. And now that we have all three terms, we can just write that dt at the end. So if we clean up this integral, 0 to 1, we'd have negative 6t squared minus 18t plus 2t plus 3 squared. Feel free to distribute that. You can also integrate it if you just condense it as 2t plus 3 squared. And then minus 4e to the 3t dt. And if you evaluate that integral, you're going to get 22 over 3 minus 2e squared. So this is a good integral to practice. That value is going to be negative, so that just means that the vector field that we have defined is working against the object that's moving along the given curve. This is also our example of a three-dimensional vector field and a three-dimensional curve as well. But we started in differential form, just to scroll back up with that dx, dy, dz. Still dealing with all the same components, it's just recognizing how they've been given to us. So, important to practice both forms of the line integrals of a vector field, and I'll see you in the next video.